Okay, this is lecture 9. This is the beginning of chapter 4, equilibrium of rigid bodies. And you'll probably find that this chapter is a little easier at the beginning than the previous material we've been covering in chapter 3. And then it'll ramp up again as we get into 3D. But I'd say overall, it's probably stuff that you're more familiar with. And what we'll be doing is we'll be applying the material that we learned in chapter 2 and chapter 3 in this chapter. So real quick, I just wanted to summarize chapter 3 because that was the slide. It should have been at the end of the last video. And I have a little word puzzle up here. You guys can figure out what that means. And just to say that for chapter 3, these are the 5 main points you should be taking away from it. And I will post a sheet summarizing this. I think it's helpful. It kind of gives a step-by-step instruction on how to find each one. And it's something that you may want to use for the midterm when you get to it. So anyway, that's chapter 3 stuff, just a little summary. So let's talk about chapter 4. Now, chapter 4, we're going to deal primarily with equilibrium. So now, up to this point, we've been talking about resultants, resultant moments, resultant forces. And now we're going to actually talk about what happens when we set all those forces or those moments equal to 0. And so and now we're going to start looking also at external reactions. So as part of our free body diagram development, we're going to look at how is the object that we're interested in, the rigid body that we're interested in the analysis, how is it connected to the outside world? So this will require looking at the types of connection points, whether they're pins, whether they're ball and socket. And so I don't expect you to memorize those, and they're listed in your book. We'll go over a few of them here, but that would be something you may want to reference for quizzes and future homework. So one of the things we want primarily to focus on in this chapter also are free body diagrams. And so these are the main steps you want to think about when you're doing a free body diagram. I know you've done them before, and sometimes you might think we overanalyze it, but if you can master the free body diagram, this is going to help you immensely in this class, but it also is going to carry forward when you take dynamics. And those of you that are MEs, you'll take intermediate dynamics also. And so this kind of material will help you. So first thing to remember is to draw the body. So you figure out what component or what part of the rigid body that you're looking at. Draw that. You want to make sure you indicate all external forces on the body. That includes reactions, any applied forces, and also any external forces, which could be, for the most part in this class, is just gravity. And then lastly, the dimensions. Now, the dimensions on a free body diagram are debatable. Some faculty say yes, some say no. I say that if they help you, put them in there. If they make things crowded and hard to understand, then don't. Because the free body diagram isn't the only thing you're looking at. You reference the original picture and you reference the free body diagram mainly so that you can identify what you know and what you don't know. So that's something that you'll have to develop as your own style. So the reaction types, these are the different, and this is right out of your textbook, page 173. This tells you the number of unknowns. So for example, at the top, where we say rollers and rockers and frictionless surfaces, you only have a single reaction, and it's always going to be normal to the surface. And so it seems to make sense because rollers can roll in the X direction according to this. Now, if you have friction, that's going to change. But for this chapter, until we get to friction in chapter 8, we're not going to worry about it. Now, one of the things, the collar, the third one down, is interesting because no matter what direction the part is sliding, and it's hard to articulate, but if you look at the picture which points to 90 degrees, it doesn't matter which direction the collar is sliding, the pin is always going to be, the reaction to that pin is always going to be 90 degrees to that slot, because any force that goes in line with the slot is going to cause it to move. Okay, and there's a couple other ones. The last one's a fixed support, and this is the only one where we can support both a moment and a force. Now, one of the things in chapter 4 is we'll be taking moments about points. That's not the same thing as supporting a moment, and I'll talk about that more as we get through it. So here is an example, just drawing a free body diagram. So in these, I would say take a moment, pause the video, and draw what you think is the free body diagram for this picture. So go ahead, sketch it out, see what it looks like, and then when you're ready, restart the video and you can see what it is. So now you're back. Hopefully you paused it quick enough. And so that's your free body diagram. So notice that we have the reaction at the end, AX, AY. Now AX, the pin that's holding at A is, because it's a pin, this beam is free to rotate. So it can't support a moment. Now, had that beam been pushed into the wall or cantilevered into the wall, then we could have drawn a moment supporting it. But because it's pinned without those ropes, it would be free to rotate. Then we have the tension, and because it's the same rope, T is the same. And the only thing we want to indicate on the T to the right is that it's at a 3, 4, 5 triangle. And then lastly, we have the weight at the end. Okay, here's another one. Now, in this case, this is a spanner wrench. This is the way you tighten and loosen round surfaces. You can't very well use channel locks on them. You're going to booger them up. So you have typically a hole in the shaft, and then at point A, there's a pin that will go into that hole, and then at B, that's just generally a point of contact that allows you then to subsequently turn. So B is a smooth surface. Now, hint, whenever you see smooth surface, that means there's no friction. And so we'll say that on and off, even though there really isn't friction in this chapter, but that's an indicator that you're only going to have a single reaction. So go ahead and write what you think is the free body diagram for this. And now let's look at it. So you notice that I had the choice of drawing the cylinder or the spanner wrench, but the spanner wrench was what the object of interest. So draw the FBD for the spanner wrench. And so at A, because we have a pin at AY and AX, then that's going to have a reaction in both those directions. The 20 pound is only going to go down, and the reaction B is only going to be to the right. Okay? So that's a spanner wrench. Let's look at another one. Here's a tape spool. Now, recall, discuss this briefly in a previous lecture, how whenever you have these journal bearings, which is what you have at A and B, then remember that you may not necessarily be able to support a lateral load. Now, unless you're told that in the problem, you don't know that per se. So in typical machinery, you're going to have ball bearings that are not thrust bearings, but because it's an unknown, don't treat it as if it is possible. So go ahead, draw that, what you think that one should look like. And again, the question is, does it support a moment? Does it support just a force? And so there's our free body diagram. So at each end, I've drawn 3 forces at A, because at A, and then I've also drawn TB and TC. Now, the way this thing's set up, they just have a single force going in the negative K direction for C and the negative Y direction for B. Now, if you were to go on, and a problem like this, if we were given TC and TB, we could solve for the reactions at A and at B. And what we would find is that DX and AX would be 0. And the main reason for that is that there's no applied force in that direction. So if you sum the forces in the x, all you have is ax plus dx equals 0. And they're equal and opposite, and there's nothing else, so they must be 0. Anyway, I don't want to get ahead of ourselves. All right, so that's the free body diagram. More practice. Each problem you'll be doing will require practice. So let's look at an actual problem. This is one I actually gave on an exam the first time I taught statics back in 2015. And after you do the problem, you'll see it's a fairly simple problem. And after you take the course, you'll look back and say, wow, that was a really simple problem compared to some of the things you've been exposed to. So here we have a truck. So we're given that it's, you have mass, you have the truck. It has 2 crates in the back, C and D respectively, 400 for C, 600 kilograms for D. And the mass of the truck itself is 2,000, centered at point G, the center of mass. So what we want to know is determine the reactions on the axles A and B. So we're ignoring friction, so really what we have is a vertical reaction at A and a vertical reaction at B, and we'll just treat A and B as a single point, even though there's 2 tires. We'll assume that the C and D are in the center and everything in the Z direction is symmetrical. So how are we going to do this problem? Let's go ahead and look at this. So here I've drawn my free body diagram. I've added a blower to the truck. So the way to think of this is like a lever. So we know, for one, is we know that if we sum the forces in the y direction to 0, we know that A and B have to equal the total of 3,000, right? We have 400, 600, and 2,000. So we know that A plus B equals 3,000 kilograms. All right. Now we can convert that to weight by 9.8, and that's not going to change anything. So we'll leave it in kilograms for now. But so A plus B is 3,000 kilograms, but what proportion is going to be what? So the easiest way to do a problem like this is to think of it as a lever. Now, if I were to draw a lever, almost like a seesaw, but a lever, then what do I know? I can write B here. Okay, B can really be at the end because there's nothing, even though there's material past here, it doesn't really have any influence because the center of gravity is back here. So we have B, and then we have a 2,000 kilogram force. So let's say 2,000 there. And then we have our 600. And then, of course, we have A. And then back here at the end, we have our 400. So there's my C, there's my D, there's my G. Okay. So now let's look at what are our distances. If I want to know the distance between C and A, then really what I'm doing is I'm taking the total distance here and subtracting this distance here, right? Because we have the total distance. And so if we want to just that from there to there, it's going to be this minus this, which turns out to be 4.5 minus 3.75, which gives us 0.75. And so by looking at the geometry, you can figure out the distance is 0.75, and this is all in meters. This distance then is 0.95. This distance is 0.85. And this last distance here is 1.2. All right. So I have my distances. So then the question is, well, how do I figure out what's what? Well, I can take a moment about a single point. And if I do that, that eliminates the moment at that point. So for example, if I take a moment about B, then B is excluded because the distance becomes 0, right? So if I say sum the moments about B to 0, then what do I have? I have 400 times 3.75 minus 600 times 2.05. And so when I'm doing this, I have the 400 is going positive, whereas the, oh wait, not minus, I'm sorry, that's plus. Sorry about that, I was misreading my notes. Yeah, so the 400 and the 600, I'm just multiplying them by the total distance from 400 to B, distance from 600 to B, and then 2,000, that distance, so plus 2,000, because all of these create a counterclockwise moment. So that's that, and then all of that equals, or you can either write equals A times this distance, or minus A times 3, because that's distance here, 3 meters, equals 0. So then I just solve for A, and I get A equal to 1710. Okay, so 1710 kilograms. Now, I know that A plus B has to be 3,000, so therefore B is 1290. And so if I go ahead, I can convert this. This ends up being 16.77 kilonewtons, and this ends up being 12.66 kilonewtons. But that's the answer. So this was just a simple lever problem. I could have subbed the moments about A after knowing B, and actually, I'm sorry, I could have summed the moments about A to find B if I wanted to, but then that would have given me 1290, and it would have been more work than just subtracting. So that's that. So that's a very simple problem, and that was the first problem on the exam. All right, so that's that. So now let's do something a little more complicated. Now in this one, we have, now before I go on, one thing I'll say is there isn't a lot to read, as you've noticed in this book. The material is really just saying sum the forces to 0 and solve. And so as such, there's not a lot of lecture per se in this chapter. And so I'm just gonna mainly do example problems of the different types. And because really the fundamentals you need have all been covered already. Okay, so let's look at this problem here. Now in this one we have a rod that's floating. It's connected, not really connected, but it's resting. B and C are supporting it, and then it's touching at A, and there's 120 pound force at it. So the question then is, how do you find the reactions at A, B, and C? And so reactions then are like I showed you. They can be as many in 3 dimensions. It can be a force in IJK. If it's in 2 dimensions, it could be a single force, depending on if there's friction, or it could be 2 forces if it's connected to the ground. So in this case, we have B, C, and A, and since there's no friction, we know that there's only going to be a single force that's normal to the surface. So again, the object of interest is this rod, so we're looking at how B, C, and A react to it. So here's my free body diagram for it. So I have A, which is pushing to the right. I have B pushing down, C pushing up. I have 120 pounds coming down here. This angle is 30, therefore this angle has to be 60 if this is vertical, all right? So that's what we're given. So we want to find A, B, and C, okay? So we're trying to find that. So I guess I should have said given 120 pounds, pretend that was written there, and I followed the rules. Now, one of the things, if you ask yourself is, well, I have 1, 2, 3 unknowns. How am I going to do this? So you want to think about how do you set up your axes. Now, if I were to take this object and I were to draw it so that it was straight, this, then I could draw my A like that. It would be at 30 degrees. Then I would draw B and C, and then my 120 pounds here. And that's 60. Okay? So I know from the problem that these are equidistant, right? This is 8, 8, and 8. Okay? So 8 feet, I believe. So 8 feet, so feet and pounds. So there I have it. So you kind of see where I'm going with this. B and C have no component in this X direction as I've written it. So I can find the A component right off by just summing the forces in the X. All right. Now, in all the problems we do, and I'm speaking of 2D, we really only have 3 equations. We have sum the forces in the X, sum the forces in the Y, or sum the moments about a point. And that's it. That's all we have. 0, 0, 0. So we have 3 equations in this case, so we have 3 unknowns. And that's how we're able to solve it. So we'll never give you a problem that's statically indeterminate. There are ways to solve statically indeterminate problems, but just not in this class. That's something you'll deal with if and when you take CE 204. So let's go, getting back to this. Sum the force in the X to 0. So what do we have? We have A cosine 30 going positive minus 120 cosine 60. And so A is 69.3 pounds. All right. So now if I want to figure out my B or C, then again, I know this. And so if I pick one of these points to take a moment about, then that eliminates that point in the equation. And then I'm just left with one unknown. So you could pick C or B, whichever tickles your fancy, but I'm going to choose B. So sum the moments about B to 0. And so in that case, it's going to be C times 8. Now because it's about B, that's going to be a counterclockwise moment, so that's why it's positive. Then it's going to be minus 120 sine 60. And that's because I'm only interested in the vertical component of this force. I'm interested in this part. This part here doesn't do me any good because it goes right through it. So one of the things is that even though this has a finite thickness, we assume it's infinitely thin for our problem. So if you're not given a dimension here, you assume that that thickness doesn't matter. Because technically, if I had a force that was going like this, and the center actually was like here, then technically you would be creating a moment over that really tiny distance d. But because we don't account for that in this simple problem, you don't have to worry about it. All right? In case you were wondering. So going back to this, so we have that minus 120, 60 degrees, and then that's times 16 feet, and then plus A sine 30, and that's times 8. Sorry, and that all of that equals 0. So we solve for C, and we get C is 1662.7 minus 277.1 all over 8, and C equals 173.2 pounds. There we go. And so then, because of the way I have it set up, because I know A and C, I can solve for B simply by summing the forces to 0. So I'm going to go ahead and sum the forces in the Y to 0. And I know that's going to be negative 69.3 times sine 30. So that's my contribution of A. And then minus 120 sine 60. That's my contribution, 120. Minus B, which is also going down. And then plus C, which is straight up 173.2 pounds. That all equals 0. And so I end up with B equal 34.6 pounds. Now, one thing I want to say is that when you start off with these problems, you assume. Now, in this case, B and C, the way that they were written, they had to be down and up just because of the nature of the reaction. But sometimes you may have a reaction where the way it's connected in the wall, like say, for example, let's say it's connected and it's cantilevered into the wall, then you don't necessarily know if the reaction AX and AY are going to go this way and this way, or maybe they're going to be negative. So we assume in most cases that these are positive. And then when we go ahead and do our numbers, if this was the case where B actually didn't go up but went down, it would have given us a negative number. So if your answer is negative when we do these problems, it means you guessed the wrong direction. And so I'll show you other examples of this, and this is something that's going to repeat itself, and it'll become especially important in chapter 6 when we talk about trusses. Okay, so hopefully that was pretty straightforward. So that's equilibrium. All right, so let's look at another problem and go back to our lecture. So now here's an example of, you have this T, lack of a better word. You have a force applied at A at 750 newtons. You have the 450 newtons applied at that point, 400 millimeters above C. And then you have BD. And so we're given the tension BD is 1300 newtons. So one thing to notice with this is that C, the way that it's on the ground, it means that it's like a telephone pole. So if you have a telephone pole in the ground, not only can it support a force, but it can also support a moment. So we have to account for that in our free body diagram when we draw it. So when thinking about your free body diagram, you want to think, what is the type of the reaction at C? Where do you cut your BD? And did you see BD was a 5, 12, 13 triangle? And so learn to recognize those because it'll make your life easier. But if you take the 250 and double it, that's 500. And if you take the 600, that's 1200. So there you have the 5 and the 12. And even the 1300 newtons is going to make the answers easy. It's going to mean it's 500 in the X and 1200 in the Y. So let's go ahead and do this problem. Go ahead. So here's our drawing again. All right, so now in this one, we look at our free body diagram. Hopefully you had a chance to maybe draw it on your own beforehand, but we know that C, because it's mounted in the ground, we have Cy, C sub X, and a moment at C. That means that the forces up here don't necessarily have to balance like they did earlier. It means that if there's more force causing this to want to rotate counterclockwise, that means that the moment here applying to this base has to be going clockwise, so it offsets it. So knowing that, we're going to include that when we set up our equations. Now, we know, for one, is that if we were to take this force here, the TBD, and let's just draw a little line here. This is our ground, and we were to extend this, that if we were to extend that, we know that this force here is 500, and we know that this component here is 1200. okay? And that's just from the triangle from the 5, 12, 13. So that means that if I have 500 down here, the 1200 component creates no moment because it goes right through C. Now, so let me come back to that. So we have 4 unknowns, 3 equations. So let's figure out how to solve this. So the first thing we're going to do is we're going to sum the moment about C. And that's a common theme with all the problems we're going to do throughout chapter 4 is that whatever point has the most unknowns, that's where you're going to take your moment about. That gets rid of it. Because if we sum the moments about that, C, then what will happen is we'll be able to determine how much moment is being applied at C, but it'll diminish our forces C. So in other words, we won't have to worry about the CYCX because they're at that point, but when we sum the moment about that point, we can calculate this applied moment that's there. So let's go ahead and do that. So sum the moments about C to 0. And the way we set that up is we're going to say 750 times the distance 500, and that's going counterclockwise. So 750 times 500 millimeters, then plus 450 newtons, and its height is 400 millimeters. So we have that. And the only thing opposing that is going to be minus 1200 newtons. And so the 1200 newtons is, and actually I wrote this backwards, I apologize. This part's 1200, this part's 500. So I have the 1200 newtons there, the 500 doesn't have a contribution, and this distance from here to here, if you look back on the original slide, was a distance of 400 millimeters. But we're not done, so 400 millimeters. And then plus the moment at C, right? Because unless this and this equal this, there's going to be some net moment. So if we go ahead and we solve, we get the moment about C equal to 75,000 or 75 Newton meters. So Newton millimeters or Newton meters. All right. So that means that this, if this were on a pin, it would fall right over. It means that without this being embedded in the ground is pushing back on this pole with a magnitude of 75 Newton meters to hold it in where it needs to be. Now, you'll notice that I wrote this moment as a positive moment. And so it means that this 1200 times the 400 was bigger than this or this, these positive moments. So my net moment is actually a counterclockwise moment. So that's important to distinguish. So because if it's the question, whether it's counterclockwise or clockwise, you want to know that. And by default, because it says 75 Newton meters and there's no negative in front, it means it's counterclockwise. Now I notice that don't be confused by the fact that when we write moment, we put an arrow over this. That's just indicating rotation. That has nothing to do with sign. All right, so now last thing, sum the forces in the X, because we want to know what CX and CY are. So if we do that, we should get negative 450 plus 500, negative 450 plus 500, and then plus C sub X. And so we get equals 0, C sub x equals negative 50 newtons. So that means that Cx is 50 newtons, but it's going to the left. All right. So I drew it, when I wrote it in the equation, I assumed it was to the right, but it's actually to the left. And that makes sense because I have 500 going this way and only 450 going that way. So that means that there's going to be an additional 50 newtons going this way that's applied to the base of this to support the thing. And then the same thing for summing the forces in the y. So in that case, we have minus 750 minus 1200 plus cy equals 0. Cy equals 1950 newtons, and it's going up as it's positive. So in that case, I did guess correctly. All right, so that's that problem. So hopefully there aren't any questions in that. I would say that with this, sometimes what we do is we'll write this going this way as a negative, which indicates that that's negative. And another way, maybe to make it a little easier, I'll try in the future, is draw the arrow going the other way. So like that. So that way I'm assuming by looking at this that that's a positive moment along with positive forces. Now you can guess whatever you want here as long as you indicate it. You could draw Cy going down, Cx going left, moment being negative. As long as you indicate it, it doesn't matter. And once you solve the problem, that will then determine whether those moments and forces, which direction they're in. And don't go back after you're done with the free body diagram and change them. But if you do have a convention that, so if you do change the convention, so for example, if I had written these Cy is going down, and if I'd written it in Cx is going to the left, then technically my answer should be positive based on this free body diagram. So if I wrote Cx equals 50 newtons, that would be correct based on the fact that I'm pointing it to the left. But that gets really confusing because then it's like, well, is it based on the free body or is it really going to the left? So what I recommend is draw your reactions always positive. And then when you get your final answer, just draw it either negative or with an arrow pointing, and then there's no question. Okay. All right, so we have one more example to do. And so here we have the Evel Knievel ramp. I put this in because I actually saw the old ramp. It's across the Snake River in Idaho. All that's left is a dirt mound now. And I remember this happening when I was a little kid, well before your guys' time. Crazy guy, broke probably every bone in his body. So anyway, so here we have a system where we have A, C, contact points at A and C, and then we have this tension BD. And so we have the 400 Newton loads at each, and we want to figure out what is the reaction A, what is the reaction at C. Now, we can see right away that A is a roller, C is a roller, so they're going to have, A is going to have a vertical reaction, C is going to have a horizontal reaction. That's not so bad. But then the question is, how do we solve those? So go ahead and look at the problem to begin with. So given the loads as shown, and we want to find A and C. All right. So how do we do this? All right. Now, this problem's a little more geometry than anything, I'd say. So I'm going to go ahead and show you the drawing that I made. And so in this case, we have, here's our free body. We have A over here, C here. We have 400 newtons drawn all the way down. We know that this tension BD here, so if this is B and here's D down here at the end, we know that at this point, this tension VD can be broken down into two pieces, the X and the Y. Okay, that'll come in later. Now, one of the things in order to solve this is as we think about this problem is if we go ahead and sum our moments about a particular point, then we're going to end up with too many unknowns. So if we look at this problem, if we try to sum the forces in the y, what do we have? We have A and we have TBDY. If we try to sum the force in the x, we have C and TBDX. If we try to sum the moments about A, we still have C and this force. So the question is, how are we going to do this? It seems like we have too many unknowns. Now, so backing up a little bit, one of the things we want to be able to do is, because TBD is as a tension in a certain known direction, we know that we can relate the X and the Y component to each other due to the triangle. And so how we're going to do that is, if I draw a vertical right here, then I know that based on the geometry of this whole thing, that this distance to this distance here is 500, and this distance to this distance is 150. And so, and I know this whole height here is 250. So I have a similar triangle, don't I? So if 500 is to 250, then this has to be 75, doesn't it? Right? It's just half. So that's half, that's half. So that's going to help. So now what I know about my triangle for TBDY is that if this is TBD, then that's 75 and that's 350, right? And so because if this is 150, the remaining distance from here down to here has to be 350, right? So I know 75, 350 are those twos. So what I can do is I can write then that TBD sub y, the force of TBD in the y direction, is going to equal 75 3/50ths of TBDX. Okay. So that's, without even starting the problem, that's something that we can see because of the angle at which the force is. So we know that we can relate those two. So that still doesn't help us with the moment, but it's a start. So if we think about our moment, let's think about structure. So one of the things let me show you is, if we go ahead and take this, notice how if I draw a point out here in space, H, notice how that gets rid of A and C if I were to take a moment about H. And that's the key to this problem is, so if you look at this, you have A and C and you have TBD, but if you take the moment about this point in space, then the only thing you have now is this force here, is the 75. And so, as I showed you before, we have 75, 350, this. I'm just showing my notes now because it's a little easier than redrawing them. And this is how I got all that. So if you want to pause the video and look at that, that might help. But that's how I got to this point. So what I've done is I've defined TBD and X and Y. I've found the point where I'm going to take my moment. So now if I sum my moment about H, and I'll come back to the image, then I know I have TBD x times 250 minus 75 over 350 TBdx times 500 minus 400 times 100 minus 400 times 400 all equals 0. Now, where did I get that from? So I'm summing the moments about h. So looking back up here, sorry, it's hard to have everything on the screen at once. So here we have the 400, and we know its distance to this point here is only 100 newtons, or I'm sorry, 100 millimeters. So this is 100. And then we found that this distance here was different, but we don't care about that at this point. So we got the 400, and then the other 400 here was a distance of a total of 400 millimeters. So that's where that came from. So we have, looking back at this, we have 400, because here's our H point way up here. So our force extends, that force extends. So we have 400 times that distance, 400 times that distance. That's why they're both negative, and 100 millimeters, 400. And so let me put those in there. Newtons, newtons. So 400 newtons, 100 millimeters minus 400 newtons, 400 millimeters. And then TBdx times 250, and then TBdy, which I substituted for that, times 500, and that's acting down here. So what this does is it allows me to find TBD. That's what I want ultimately. So I determined that TBD, in this case, is equal to 1,432 newtons. All right. And so, sorry. So that's that. So I'd say go through, I know I went through that quick. It's hard. It's a lot harder on video than, I apologize. It's not as easy to do this problem. So I'd much wish I was in front of you guys at this point. But so looking at that, you can hopefully see where I got those numbers from. Again, I sum the moments about this point up here, H. That's all. I just found that H. Now I need to find A and C. So to do that, then I just sum my forces. So I know A minus 400 minus 400 minus 300. And that's because if TBD is 432, and I go back and I find its X component is equal to 1400, its Y component is equal to 300. And so what I did is I just converted those back. I found A is 1100 going up, and then minus C is 1400, just equal to the X component. And that's that. I have the reactions. Okay, so hopefully that made sense. And there's the drawing of it big. Oops. And so again, just real quick comment, as you're looking at this diagram after I've gone through that, you can see the upper corner is where I took the moment, the 400 newtons times 100 millimeters, the other 400 times 400 millimeters, respectively. And then the TBD was applied down in the corner. And so that's where I got the 250 for the horizontal force and the 500 for the vertical force. Okay, so hopefully that makes sense. That's the beginning of this. Now in lecture 10, I'm going to continue doing problems like these. So don't despair, we'll do more examples, and then we'll jump into 3 dimensions. Okay. And we're coming up on the exam, so that's going to be in the next week and a half or so. So I'll let you know more about that soon. Thank you very much for listening, and I'll see you in the next lecture.